Hi there, students. I'm going to talk to you about the image intensifier. That's the main component of your fluoro unit. So just a little something fun for you there. And the objectives here. So here is your basic setup. You have the fluoro tube under the table and your image intensifier above the table. This is similar to the unit that we have in our lab. Up above that is the TV camera. We're going to talk about that next week. So the image intensifier is an electronic device that receives the image-forming X-ray beam and converts it to visible light. So conventional fluoroscopy without image intensification has two serious limitations. It produces a statistically inferior image, and the light is too dim for daylight vision. So the design, the image intensifier tube is an evacuated glass envelope, just like with our normal X-ray tube. It's also called a vacuum tube, which provides a structural support. It maintains the vacuum and is mounted inside a metal housing or container to protect it from rough handling and breakage. So very important things for you to remember. The vacuum tube contains four basic parts. Those are the image, so the input phosphor and the photocathode, the electrostatic focusing lenses, the accelerating anode, and the output phosphor. We're going to cover each of those in this lecture. So the input phosphor. So first generation intensifier tubes had silver activated zinc cadmium sulfide crystals in the output screen. So it's second generation, that's what we're currently using today, has cesium iodide as the input screens. So it provides a lot better detail for us and a brighter image. So the input phosphor is the remnant radiation is transmitted to the glass envelope and interacts with the input phosphor. So the energy is converted into visible light. So when it hits the input phosphor, the photon, it's converted to visible light. So the fluorescent material is deposited on a thin substrate of the glass, and when it's hit, light is given off. So when a photon hits it, light is given off. So why do we do that? It's the purpose of converting incident X-ray photons to light. That's the whole purpose of the input phosphor. So cesium iodide crystals are on the input phosphor and approximately 5 micrometers in diameter and are packed tightly. So they're like little pipes that transmit light. So with those little pipes, the resolution is increased. The photocathode. So the photocathode is attached to the input phosphor by adhesive. So it's transparent, and the photocathode is made of a combination of antimony and cesium compounds. What it does is it takes the light from the input phosphor and converts it to electrons, also known as photoelectrons. So it's in proportion to the intensity of the light that it receives. So it produces as many electrons as light that it receives from the input phosphor. So this process is called photoemissions or photoelectric emissions. So here's your general diagram. So here's your input phosphor is the yellow, and there's adhesive holding the photocathode onto the input phosphor. So remnant radiation comes up, so a photon hits the input phosphor and it converts it to light. It hits a photocathode, it takes the light photons and changes them to electrons. So this is electrons in the beam here. So the photocathode is also the cathode of the image intensifying tube. What happens is when the electrons are coming out of the photocathode, the anode is accelerating and it has 25,000 volts. So the voltage or difference in the electrical potential between the cathode and the accelerating anodes, the electrons fly across the tube to the output screen at a very high rate of speed. And what happens is they are streamlined to focus in to a focal point with the electrostatic lenses. So they're located along the length of the image intensifier, and an increase in voltage to electrostatic lenses will cause the electrons emitted from the cathode to be focused to extremely fine beam, and they come to a point called the focal point. So the electrons arrive at the output phosphor with the high kinetic energy and contain the image of the input phosphor in a minified form. The accelerating anode is located at the neck of the image intensifier. It's a circular plate and it has a hole in the middle so the electrons can pass through to hit the output phosphor. The accelerating anode draws electrons from the photocathode and accelerates them towards the output screen with approximately 25,000 volts. So here's the diagram. We have your input phosphor, your photocathode, here's your electrons, these are your electrostatic lenses, and then here's your focal point right there, and as you can see, this part right here and right here is your anode. This right here is your output phosphor. So your output phosphor, when the electrons strike the output phosphor, energy is converted back to light photons. So it comes into the input phosphor as photons, it is changed to light photons, hits the photocathode, and it changes to electrons. There's 25,000 volts applied with the accelerating anode, and the electrostatic lenses take it to a focal point. And at that focal point, they pass, or just after that, they pass through the anode and hit the output phosphor. So when it hits the output phosphor, it's changed back to light photons, thousands of times brighter than the input phosphor due to its smaller size and additional energy given to electrons when they are accelerated through the image intensifier. So it's usually made of zinc cadmium sulfide, and modern intensifiers are constructed with a 1-inch or 2.5 centimeter output phosphor. That's pretty standard. Okay, so that's the basics on how the tube works. Make sure you understand what happens when a remnant beam photon comes in and what leaves the tube. Okay, thank you. Study up.